Hello, and welcome to this video where we will be now looking at multi-particle system as we have said in the last video. Up until last video, what we have described or tried to explain is on the basis of a single particle, but in the realistic sense, uh, the systems always exist in more than one particle format. So therefore, it's important to understand the concept also with respect to more than one particle and its corresponding states. So what we call as an assembled system. For example, let's try to decipher this classically. Imagine that you have two particles which are independent of each other and which are represented by the configuration marble 1 and marble 2. Each particle can be independently found in various states. For example, A and B both in yellow and marble 2 A and B in blue. To define that, it is described as the vector representation. So for example, x1 and x2 represents the probability of finding marble 1 at A and B and respectively. Also, to further mathematically evolve this, we have constructed the operator for it in terms of matrices. For example, M1 and M2 with the value of probability corresponding to the probability of the particle being found in a given state. Now, when we combine these two particles, that would be easy, as you have seen in the course of linear algebra. We can achieve by Kronecker product or the tensor product, and we then represent a combined system where marble 1 and marble 2 are combined with each other, and now instead of having a vector of two states, we will having a vector with four states. So A1 with marble 1 with respect to marble 2 in state A, marble 1 in state B with respect to marble 2 in state B, etc. We can further infuse the matrices, that the probability matrices that we have defined, and there we will end up in having a four-dimensional representation of the assembled system in a mathematical term. So how to do the Kronecker product is defined in the video for the in the series of linear algebra. You must have a look at it, but it is not a very difficult exercise to do. Now here, what it now represents as the vector with four dimension, also because of the each state transition that it has. So it has now 16 entries where the particles probability with respect to each other being found is described. So if you now take it as an evolution, for example, how the system is evolved, let's assume that the particle, the state, initial state is at the vertices 1, where it's represented by 1 and rest all other entries are 0. If you now multiply this with the matrix product of the combined state, the Kronecker product, you will see the final state coming on the right side. Now, this is the mixed final state. What you can do is also reverse it in a way that you can apply the reverse step and then try to decompose the system as to its constituent particle. So if you see how this is done step by step from left to right, we have now decomposed the system with their individual vector representation is still marked as a product of Kronecker. Now, this is a very unique case in terms of that we are able to decompose a system, and if you move this concept further away to quantum, the mathematics will remain the same as we have seen in a case of classical. The only difference is with classical, we are with quantum, we are not dealing with L2 normalized vector and unitary matrices, while in the case of classical, we mostly deal with L1 and probabilities. However, it is also to be noted, for example, here is an example of a quantum system where both the particles on the left has been in superposition, which is needless to say, and then you can end up again decomposing the way we have seen in case of the classical example, the system into its constituent components. But this does not hold in all the cases, and that's where the beauty of quantum and the characteristic of quantum comes into picture. Look at this example. If you now try to decompose this system represented by the matrix vector representation of 1.5, 1.5 at 1 and 4 and rest 0, it will be impossible to compose. It cannot be decomposed, and that has led to a new phenomena, or the characteristic of quantum assembly, which we call as quantum entanglement. What does the quantum entanglement do? Is actually help us observe a state of one particle, giving us the capability to know the state of the second particle as well, which means they are entangled in their state representation, and therefore knowing the value of one leads directly to us to know the value of the second. Now, quick final remark on entanglement, which is a very useful property, is that a state that cannot be factored as a product of states. So that's why you cannot take a reverse step. There are no individual particles, though they seems like, for example, in superimposed, but they are inseparable as a whole. It is possible to break the entanglement through interaction, for example, after measurement by applying certain techniques, but overall, entanglement does represent very core of quantum capability and the feature of quantum capabilities. So I hope you liked the example of this assembled system and be able to decipher now between what's the difference between a superimposed and an entangled system. I'll stop here. Thanks for watching, and I'll hope to see you in the next video. Thank you very much.